Hi everyone, in this video we're going to go over the relative integration of signals in NMR. So last time we talked about how to determine the unique protons on a molecule. So for example, we saw this alcohol and we figured out that essentially each atom had its own unique protons. So we had 3 HA protons on the first carbon, 2 HB protons on the second carbon, and then the proton on the oxygen was in its own unique chemical environment as well. So on an NMR spectrum, what we would find is 3 different peaks, so 3 unique signals. So we would have one kind of near 0 parts per million. We'd have another one kind of in the middle there, and then one by 5 parts per million. Now, what chemists will do is they'll use a software and integrate each of those peaks and determine the area under the peaks. The area under the peak will tell us the relative number of protons that we have in our molecule, or rather, the relative number of HA protons versus the relative number of HB versus the relative number of HC. Now, don't worry too much about where these peaks are located. We'll talk about those locations later, so the parts per million, just kind of ignore that for now. But let's just make a note. So chemists will integrate each peak to determine the relative areas, the relative areas under each peak. So what you might see on, for instance, an NMR printout or NMR spectrum, underneath they'll list the different peaks with their parts per million values, and then they'll also list the integration value. So let's just list our 3 different protons. And we might see something like 3,000 for HA, 2,000 for HB, and 1,000 for HC. So those would be the areas under the peaks. But we obviously do not have 3,000 HA protons or 2,000 HB protons, etc. So what we do, or what the software will do, is divide by the lowest value. 1,000. And then that will give us the relative amounts of each proton. Now, luckily for us, this does equal the actual amount of each proton we have in the molecule. So we do have 3 HA protons, 2 HB protons, and 1 HC proton. But this might not always be the case. For instance, you might have to round or factor in a value of 2, so you might have to multiply everything by 2 to get the actual amount of protons. It just kind of depends on your molecule. So let's look at a different molecule. So let's look at a benzene ring that has 3 tert-butyl groups attached, and they're all equally spaced. So what I would like you to do is figure out all of the unique protons on this molecule, and then we'll talk about the integration. All right, so see if you can figure out how many unique protons this molecule has, and you can pause the video, and when you unpause, we'll go over it together. Okay, so I'm just going to draw in the 3 protons that are on the benzene ring. And then we know that each of these little methyl groups here has 3 protons as well. But I'll just circle them since it would be kind of busy to draw all of them. All right, so let's look for planes of symmetry because that will help us figure out if we have protons in different environments or in similar environments. All right, so it looks like actually there might be multiple planes of symmetry here. We have one going directly down the middle, but then we also have one going this way and this way. Okay, so what that tells me is the 3 protons that are directly bonded to the benzene ring are all the same. So I'll label those HA. And then all of the protons that are on those methyl groups are all the same. So I'll label those B. So we have HA and HB. All right, so the NMR spectrum would have 2 unique signals. So I'm just going to kind of draw generic peaks, but we won't worry about where they're located. We'll just worry about their size. So again, chemists will use a software to integrate these peaks. So I'll draw little integration signals there. And the area under the smaller peak, let's say, is 1. And then the area under the bigger peak would end up being 9. So it's 9 times larger. So let's add our integration information here. So we have a 1 to 9 ratio between HA and HB. But looking at our molecule, we actually have 3 HA protons and we have 27 HB protons. So again, these integration values give us the relative amounts of each proton, but it doesn't give us the exact amount. So let's make a note. So integration values give relative ratios, not exact amounts. So just something to keep in mind when you're looking at NMR spectra, if you are given integration values, those might not necessarily be the exact amount of each proton you have. It's just the relative amount. So here we'd have to scale everything up by a factor of 3 to get the exact amount of each proton. Now, really, the only way we would know that is if we had the molecular formula. So the molecular formula, let's see, that would be C6, 7, 8, 9, 10, 12, 13, 15, and H30. But if we didn't have the molecular formula, it would be much more difficult to kind of figure out how many, or the exact number of each proton. So just something to remember. Now, so far I've been drawing each of my signals as single peaks, but peaks can actually, or these signals can actually have multiple peaks. So that's called multiplicity. So far we've been looking at what are called singlets, where you just have a single peak, but a signal could also be split in 2, which is called a doublet. So you have 2 peaks in your signal. You can also have what's called a triplet. You could have a quartet, and so on. Now, why is that? Why would we get these different signal shapes? Well, it has to do with that nuclei spin that we talked about. So nuclei can be spin up or spin down. kind of similar to electrons. And because nuclei can either be spin up or spin down, they can have what's called spin-spin coupling with neighboring nuclei. So for instance, if you have a proton on one carbon and then a proton on the neighboring carbon, they can couple or spin-spin couple with each other, and that can create multiple peaks. So down below I have a little diagram of the different spins that nuclei can have. So remember, if a nucleus is in an external magnetic field, so again, nuclei can generate their own magnetic field just by their spin. Oops. Sorry, I hit the next button. But if we apply an external magnetic field, then the nucleus can either align with the applied magnetic field or against the applied magnetic field. Now, if the nucleus is aligned with the magnetic field, it's in a lower energy state. If it's applied against the magnetic field, it's in a higher energy state. So it takes more energy for a nucleus to be aligned against that external field. So this is kind of the same thing with neighboring protons. They can have the same effect on each other. So let's look at some examples. All right, so let's say we have two carbons and each one has one proton, HA and HB. So they're in different chemical environments. Now let's focus on HB. So let's say that HA is spin up. Now there are two possibilities for HB. HB could either align with HA or against HA. So it's like HA is the external magnetic field. So this would give us two peaks in our signal with a 1-to-1 ratio. And that's what would give us our doublet. And we'll just give that the symbol of a lowercase d. So if we had a sample of this molecule, whatever it is, and we ran it through an NMR spectrometer, some of the molecules would have an HB proton that was aligned with HB, or HA, excuse me. Some of the other molecules would have an HB proton that was aligned against HA. So that's why we get this two-peak signal, because some of the molecules have two spin-up protons. Some of the molecules have one spin-up and one spin-down proton. So we get these different energy levels. Now let's make it a little more complex. Let's say that we have one HA proton again, but this time we have two HB protons. So what would happen? So again, let's say that HA is spin up. And then we're looking at its neighboring protons, HB. Now both of those HB protons might be spin up. So they're both aligned with HA. Or one might be aligned with HA and the other is aligned against HA. Or they might be the opposite. So the first HB proton might be spin down, the other one is spin up. So there's two possibilities there. And finally, the last possible state is that both HB protons are spin down. So now we have this ratio of 1-to-2-to-1, and HA will show up as a triplet. And the central peak is going to be a little bit taller than the outer peaks because of that 1 to 2 to 1 ratio. So HA is feeling the possible effects of those HB protons and coming out as a triplet. So remember, this is the peak for HA. Now let's make it even more complex. Let's say we have, again, HA and its spin up. HB, and let's say we have 3 HB protons. Now it gets more complicated. So all 3 HB protons there could be aligned with HA, or maybe one is aligned with and the other 2 are aligned against. But again, that could depend on which HB is aligned with. So we have 3 different options here. What if 2 of the HB protons are aligned with HA? Well, we still get 3 different scenarios there. And it depends on which of the HB protons are aligned with HA. And then finally, we could have a scenario where all 3 HB protons are aligned against. So we get a ratio of 1 to 3 to 3 to 1, and we end up with a quartet for HA. So neighboring protons will have an effect on the type of signal that our original proton has. Now, this can get even more complex. So, for instance, you can have sextets where you have 6 peaks in your signal. You can have a septet where you have 7 peaks in your signal. You can also have what's called a multiplet. And multiplets are basically just a combination of different peaks. And it's basically just a bunch of noise because the molecule is so complex that it's hard to read what that signal is. So it really depends on the molecule that you have. So one thing to notice here is the peak for HA really depends on how many neighboring protons it has. So in our first example, HA had 1 neighbor, and it came out as 2 peaks. In the second example, HA had 2 neighboring protons, and we ended up with 3 peaks in our signal. And then in the last example, we had 3 neighboring protons, and it came out as a quartet, so a signal with 4 peaks. So this is called the n+1 rule. So let's just make a note. So we can use the n+1 rule to predict peak splitting. So for example, if you have 3 neighboring protons, that's going to give a quartet. So you'll have 4 peaks, or n+1 peaks, in your signal. All right, now one other thing that we should take note of, or there's a couple of other things we should take note of. HA can only feel protons that are 2 to 3 bonds away. So, for instance, I was showing 2 protons on neighboring carbons. So those would be 3 bonds away from each other. All right. And then HA cannot be split by other HA protons. So if you have two protons that are the same, they cannot split each other. So equivalent protons cannot split each other. And then finally, let's say we had a proton bonded to an oxygen. That proton will not split the original proton. So HA will not be split by a proton bonded to a non-carbon atom. So again, if you had an alcohol, the original proton, HA, will not be split by the hydrogen on oxygen. Okay, so let's actually go back to our original molecule that we were looking at, the alcohol, and let's just try to figure out which type of signal each proton would have. So this is the NMR spectrum for that molecule we were looking at earlier. And remember, this molecule had 3 unique protons. And in the NMR spectrum, we have a triplet, a singlet, which I'll abbreviate S, and a quartet, which I'll abbreviate Q. So let's figure out which proton would go with each signal. So HA, HB, and HC. Which signal do we match those to? All right, so if you want to try this on your own first, you can pause, pause the video, and when you're done, we'll go over it together. All right, so let's focus on HA. And remember, HA cannot be split by other HAs. So I'm just going to draw one HA, and then we'll look at those 2 HB protons. So those are the 2 neighboring protons, and using our n+1 rule, we have 2 neighboring protons, and then we'll add 1, which gives us 3. So that would tell me that HA would produce a triplet. So we'll just write HA next to the triplet signal there. Okay, now let's focus on HB. And remember, equivalent protons won't split each other, so I'll just draw one of the HB protons. And the neighboring protons are those 3 HA protons. Because remember, HC, even though it's 3 bonds away, HC is on an oxygen atom. So it's not going to split HB. So only HA will, because it's on a carbon atom. Okay, so in this case, we have 3 neighboring protons. So let's use our n+1 rule. So 3 + 1 = 4. So that tells me that HB is going to produce a quartet because it has 3 neighboring protons. All right, and then looking at HC, oops, it's on its own atom, an oxygen atom, which is a non-carbon atom. So it's not going to be split by anything. It's not going to split anything itself. So it's just going to give a single peak. So that will be the singlet. All right, so let's just make a little chart of what we've learned so far about this molecule. So we talked about the integration values initially, and then we talked about the multiplicity. So we said HA had an integration value of 3, HB had an integration value of 2, and HC had an integration value of 1. And then we figured out that HA, the signal for HA would actually be a triplet due to the 2 neighboring protons. HB would be a quartet because of its 3 neighboring protons, and HC would be a singlet because of its because it's bonded to a non-carbon atom. So it's just kind of by itself. Okay, so let's do a challenge problem. Let's predict the number of unique protons, their integration, and their multiplicity for a particular compound. So I'm going to draw the compound down below. So we've got a benzene ring, and then we've got those 2 groups attached, so isopropyl and bromine. So see if you can find all of the unique protons that exist on this molecule. And one hint, look for planes of symmetry. That will help a lot. And then try to figure out the relative integration and the multiplicity. So whether each proton would have a singlet, a doublet, a triplet, etc. And when you're done, we'll go over it together. Okay, so the first thing I'm going to do is look for any planes of symmetry, and I do see one plane of symmetry just kind of down the middle here. So that will help. And then I'm going to draw my different protons. So we have one proton kind of in the middle up above. So I'm going to call that HA because it doesn't look like there's going to be any other similar chemical environment. And then we've got these 2 methyl groups with their own protons. And because we have that plane of symmetry, I know that the protons on either methyl group will be the same. So I'll just label all of those HB. Then I know that there is a proton at the top of the benzene ring on either side, and there's also protons on the bottom on either side. Now the protons on the top of the benzene ring, they're in their own chemical environment compared to the protons on the bottom. So the protons on the bottom are both much closer to bromine than the protons on the top, and that's why they're going to have a different chemical environment. So I'll label the 2 top protons as C and the bottom ones as D. So again, the HD protons are closer to bromine, and the HC protons are further away from bromine. So they have different chemical environments, which makes them unique. All right, so let's make a chart of the different unique protons, their integration, and their multiplicity. So we have HA, HB, HC, and HD. So it looks like we only have one HA proton, so I would assume the integration value would be 1, or the relative integration value. Then we have 6 HB protons, we have 2 HC protons, and then 2 HD protons. Now, none of these are, none of these have a common factor that we can divide them by. So this is probably our relative integration value. All right, so now let's predict the multiplicity. So let's focus on HA. How many neighboring protons does HA have? Well, remember, it can only be split by protons that are 2 to 3 bonds away. So the HB protons are all 3 bonds away. So 1, 2, 3, for example. What about HC? How far away are those bonds, or those protons? So those protons are, let's see, 1, 2, 3, 4 bonds away. So those are too far away to be neighboring protons, or to have spin coupling with HA. So that means HA has 6 neighboring carbons. Okay, so 6 plus 1, 6 plus 1 is 7. So that would be a septet. So that would look kind of crazy. That would have, let's see, 1, 2, 3, 4, 5, 6, 7 peaks in a single signal. So it is possible to have these really divided signals. Okay, so now let's look at HB. How many neighboring protons does HB have? And again, let's just focus on one of the HB protons, because remember, protons that are in the same environment cannot split each other. So how many neighboring protons would HB have? Just one, and that's HA, because, I'll use a highlighter here, we have 1, 2, 3 bonds away, and HB would be way too far away from HC in order for it to be split by HC. So HB only has one neighbor, so that would be 1 plus 1 is 2. So that would be a doublet. So the doublet would kind of look like little vampire fangs coming up. All right, now let's focus on HC. How many neighboring protons does HC have? Well, we already said that HC is too far away from HA or HB to be affected by them or to affect them. So we have to look elsewhere. So the next neighboring proton would be HD. So it looks like HC only has one neighboring proton. So 1 plus 1 is 2. So that would be another doublet. And now what about HD? How many neighboring protons would HD have? Just one. So again, we'd have 1 plus 1 is 2, so we'd have yet another doublet. So on our NMR spectrum, we would expect to see 4 unique signals. One of the signals would be a septet, and the other 3 signals would be doublets. All right. So this is kind of fun to do. It's like a little puzzle with its own set of rules that you have to follow. Next time, what we'll do is we'll look at these ppm values, and we'll kind of talk about where we expect these different peaks to show up on an NMR spectrum. Do we expect them to show up at lower values or at higher values? And it kind of depends on whether you have, for instance, electronegative atoms like oxygen, or if you have a benzene ring present, that can affect where your peaks show up. So we'll talk about that next time. I'll see you then.